Hi, this won't be a terribly technical talk. I've been engaged for many years in learning about various space missions or other business in space flight, and then boiling down the technical stuff and taking it to the public, planetariums and astronomy clubs and science fiction conventions and whatnot. So I hope you won't be disappointed if I don't get very, very scientific here, but it's sort of a general introduction to what Clementine did. And I'm facing a more sophisticated audience than I usually do, so go ahead and ask a question if you have one, and I'll try to handle it. I like questions right in the middle of the talk. The Clementine mission flew last year, launched it in January of 1994, and suffered a massive failure in the first week of May of 1994. So it operated for a few months and didn't quite complete the mission that was hoped for it. But the spacecraft still exists and is still working to some extent, and it really was a great success in the major purpose and in its minor purpose. I guess my interest in it as an NSS guy is that Clementine was the first U.S. spacecraft launched specifically to explore the moon in about 20 years. Here's one logo and showing you a picture of the spacecraft. Probably there are slide controls here somewhere. But they're not plugged in. Yes. Yes, okay. The Clementine was a project of the U.S. Department of Defense. Yeah, there she is. And we should turn the lights down. Someone will be good enough to play with the lighting controls.
Other ones.
Yeah. This is a little surprising, and the basic story, to go over it quickly, is that Clementine was not launched by NASA, which usually has the mission of exploring the planets, but rather by the folks who are supposed to develop weapons that shoot down missiles, the Ballistic Missile Defense Organization in the Pentagon. And in cooperation with a couple other agencies that develop the hardware. And over the years, in the years that we've had a Strategic Defense Initiative program going, changed its name a little later to Ballistic Missile Defense, but over those years, the problem of missile defense has been broken down into detecting the missiles and then figuring out a way to shoot them down, right? And so many billions have been spent on developing hardware that would achieve some of those goals. And among the ingredients, it was clear that you needed a system of satellites that would at least orbit the Earth and look down and try to spot any missile launches with a great deal of energy appearing somewhere on the Earth. Well, so that would take a lot of satellites, probably, and if the Star Wars system was going to need lots and lots of satellites, then the price tag would be very high unless the satellites were small and inexpensive, right? So a priority in the SDI program was to develop lightweight hardware and hopefully inexpensive hardware for spacecraft. And a number of organizations worked very hard to get all the things you need to build satellites smaller. The power systems, the computers, the navigation and guidance widgets and so forth. Eventually it was about time to flight test all of these things in space. So Clementine became a spacecraft that was a test bed for new sensors, new hardware of various kinds. Here's a strip of showing one of what typical Clementine picture, a narrow stripe as it orbits the moon. Just a minute of introduction to those. And a picture of the moon. And I'm not starting this talk out at all the way I thought I was going to start it out. So this new hardware was designed to go aboard a satellite. The idea of Clementine was well, let's put it in Earth orbit maybe, and then launch some rockets, or have it chase some satellites, right? Well, launching rockets or satellites for it to chase would cost real money, and somebody got the idea, why don't we send the spacecraft to track a natural object in space? That way we can explore space at the same time we're testing out our sensors and testing out our all of our satellite systems. And so Clementine, although its chief purpose is to test gadgets, try out gadgets, and it has far more new technology aboard it than one would expect in a scientific spacecraft. It had the secondary objective of visiting the moon, and as we'll see, also visiting an asteroid, and gathering a lot of scientific information about it. And that's that's good news to me, and good news to other people who are interested in the moon, because the last Apollo spacecraft left the moon in 1972, and the Russian program terminated in a few more years, and these programs brought back a lot of scientific information about the moon, but you know how scientists are. They have the answers to some questions, that only asks them causes them to ask a lot more questions. So in the years after Apollo, scientists who were interested in the moon wanted to have further missions, and both in NASA and the European Space Agency, missions were proposed. Let's build another spacecraft, go to the moon, answer some of the further scientific questions. Here's a proposal from the middle 80s called the Lunar Geoscience Orbiter. There was an attempt in the late 70s that didn't go anywhere in NASA, an attempt in the middle 80s that didn't go anywhere. ESA had a study in the late 70s. And to put such a project in the pipeline of NASA's exploratory missions never really worked out, because Jupiter was very important, and Mars was very important, and Venus was very important, and the projects to study those planets kind of won out. So lunar scientists were feeling pretty lost and unhappy by the late 80s. To jump ahead a little bit, the late 80s were when the Lunar Prospector project got underway, and as you may know, the Lunar Prospector project has now been adopted by NASA as the next Discovery mission, and the one that NASA wants to fly in the near future. So we may have a happy ending yet on this. But in the meantime, the DOE folks invented Clementine. And Clementine was run pretty fast and with a pretty tight management team, and for quite a low cost. The whole project, including the launcher, runs to about $75 million. And as I said, even the Pentagon folks really had the job of testing out new technology for weapon systems, but secretly they wanted to be space cadets and explore the universe, right? So a lot of these things are combined in this logo. This project is very logo happy. This is the second logo we've seen already, and you see Clementine herself, the daughter of a miner 49er. You can tell that she's a miner's daughter because she has a pick over her shoulder, and she's carrying a shield. Doesn't make sense very much, but the shield is the logo of the Strategic Defense Initiative, or BMDO, right? Okay, so that's why she has a shield. And she's standing here over the moon, a moon which has a little American flag on it sticking out. And behind her shoulder, there's a big red rock, the asteroid known as Geographos, which came near the Earth in August of 1994, and which Clementine hoped to visit. And you can tell that she's left her footprint on there because there's a number 9 on the rock. So unfortunately, she's not quite lost and gone forever at this point, but she's not much use to anybody. Here's a slide that is slightly too busy that shows you a picture of the spacecraft, a large bipropellant motor on the top here for kicking it into orbit and doing major maneuvers. There's a thruster system that's a monopropellant set, and a list of the new sorts of gadgets that have been stuffed into this thing. And as you can see, a list that's surprisingly long for spacecraft. But Clementine was intended to be risky, intended to be trying out a lot of new stuff. A new kind of solar arrays, a gallium arsenide uranium solar array, nickel hydrogen batteries, which haven't been flown in space, or at least not very often. The central computer was a standard 1750 processor that has been used in other spacecraft, but there's new exciting hardware RISC processors to do jobs that aren't absolutely essential to the spacecraft, such as image processing and such. And they use a couple of gigabyte solid-state memory instead of a recorder, magnetic tape recorder with moving parts to record things. And to determination, hardware includes there's a fiber optic gyro and a ring laser gyro, new gadgets for sensing the orientation of the spacecraft that have been developed for missile defense. New lightweight reaction wheels, fancy new structures and such. Another view of the spacecraft just to show you that the general layout of it, the fuel tanks down here, solar panels, and a platform here that contains sensors. And we'll take a look at the sensors in a little more detail, but they're all very small, lightweight, very interesting sensor hardwares in a variety of bands that might be useful in missile defense, but are also useful for looking at the moon or looking at an asteroid. Well, I'll go over that list in some more detail later. Here's the people who put it together. By the way, now and then you see a button like this, which says audio, and that's because I swiped some of these illustrations from the CD-ROM, which I had here just a minute ago. Well, from the Clementine CD-ROM that the Lawrence Livermore lab put out. Let's see, they're here. Livermore was responsible for most of the sensor development. The thing was principally administered by BMDO. They got the Naval Research Laboratory to build the spacecraft and integrate gadgets from other places. They got help from NASA in a variety of ways. They asked NASA to appoint scientists to analyze the lunar data. Okay, so some of the usual suspects in lunar geology, lunar geophysics, are on the list of investigators, and they got help from Goddard and from the Deep Space Network and JPL for planning the asteroid encounter. Here's what the spacecraft looks like. It's more or less a couple meters tall. There's an interstage that attaches it to the Titan II rocket, which was also instrumented and flew on its own separate trajectory in cislunar space. It's all folded up, and now you see the reason that there were peculiar holes in the solar panels. That was the best way to fold them over the antennas and still have the antennas peeking out here. Let's see. And as I said, on the 25th of January, 1994, Clementine blasted off and went into peculiar orbit where Clementine made a few revolutions and waited for the moon to show up in its trajectory. So it took several weeks rather than a few days to get to the moon, but it finally went into lunar orbit a month later, and in February. Can we focus this slightly better? What if you press this audio button? It doesn't do anything. Yeah. So it spent 71 days in lunar orbit. A couple of months passing over the moon in a polar orbit, a standard mapping orbit, and trying to cover with its cameras every inch or almost every inch of the moon. He did a nice thorough job there, and what was supposed to happen was that it would inject itself into a trajectory that would take it past the Earth again, so sort of return to the Earth, swing by it, and use the Earth's gravity to pick up a little energy and do the same thing again on the next pass to the orbit, and another swing by the Moon, and through these complicated maneuvers, get onto a trajectory that would take it past the asteroid Geographos at the end of the summer. Unfortunately, there was a failure that occurred on May 7th after Clementine had left the Moon and visited the Earth. This is a diagram of the orbits the orbit that right after launch, where Clementine goes into orbits like this, and then goes into wide elliptical orbits that's called phasing loops that are waiting for the Moon to show up in its orbit, and it does lunar insertion sort of a month after launch. Let's see here. Here's what the mapping business looks like. The notion. Yes. Okay, I can almost reach it. Thank you. Yes. That was a near disaster. We're gonna have a real disaster before the end of the talk. You can look forward to that. Probably most of the people in this room know why a polar orbit is a good idea for a mapping spacecraft, but I'll say anyway. The Moon is rotating, of course, this way, and if the spacecraft is in orbit over the North Pole and the South Pole, as the Moon rotates, the spacecraft will eventually pass over every part of the Moon in about half a month. It'll pass over every part of the Moon that's illuminated in 1 month, and if the spacecraft orbits the Moon for a couple of months, then you get an opportunity to make nice overlapping picture strips for pretty much the whole Moon if your cameras are wide angle enough. This is the slide to remind me to talk about the disaster. This reliable, good old Bill Standard 1750A processor failed, or maybe the processor didn't fail, but maybe the software really wasn't completely debugged because the mission was developed in a big hurry. And a complicated, while Clementine was doing a test, it was now far away from the Moon and on its way back to the Earth. It was looking at the Moon and performing a test where it targeted on the Moon and tried to use a new tracking algorithm to keep a target in its sights. Of course, it was possible to fire the attitude control jets during that exercise, right? Well, the program counter unfortunately jumped into a place that switched on the attitude control jets, and they used up all of their fuel in a remarkably short time, leaving the spacecraft spinning at 80 revolutions per minute. As one engineer put it, not good. So there were attempts made to try to use the main bipropellant motor to give it a little twist or de-spin it somewhat or try to get it under control. But basically the attitude jets and the maneuverability that they needed in order to put Clementine into its trajectory to go to the asteroid were lost. So Clementine went into a solar orbit instead, and wound up losing power because the solar panels were no longer oriented properly towards the sun, and the power budget went way below what Clementine needed to communicate with the ground. In the last month or so, I guess, the ground stations have recovered the spacecraft as time went by and it gradually rotated into the proper attitude again. So for a while, we have it working again, and there was, and the reports from the Clementine's operators are that it's working fairly well, and that they're pretty happy with the long-term performance of the widgets that they've been testing out. I haven't seen any details on that, but we'll probably hear something in the technical press, I presume in the future. Well, the array of sensors aboard Clementine is important in understanding the kind of information Clementine would get. It's pretty much just an imaging spacecraft, and not anything. There's a little bit of radiation experiment on board, but it doesn't do, for instance, the geochemistry experiments that you would like to do with a gamma ray spectrometer. Lunar Prospector will do that, and maybe I'll talk about that later. But the imaging experiments are nice and really expand the capabilities that we had from Lunar Orbiter and the Apollo camera coverage of the moon, which is that's the data set we have from this kind of thing. What the first imaging device aboard Clementine is a star tracker, and while it's not really great for studying the moon, it does produce some nice postcard pictures, and it's a novel device that has a wide field and can see fairly bright stars, and then try to figure out where have I seen that pattern of bright stars before. Here's a line between two, here's another line between two, and there's so much angle, and there's another one over here, and it's got this angle to the first one, and let's see, could that be, and it goes through some giant planetarium it has in its memory and finds that this is the Big Dipper. There's an ultraviolet / visible camera. I don't know why they couldn't have thought up a better name for it, because that's a big mouthful. But the camera that works pretty much in the optical wavelengths, with a little bit into the ultraviolet and a little bit into the near infrared, and it's only a few inches long, as you can see. CCD chip, pretty much equivalent to a standard thing you have in your camcorder at home. And just much lighter in weight and taking much less power than cameras have done aboard spacecraft in the past. Here's an image of a crater, the crater Nansen near the North Pole of the moon, from the UV visible camera. All of Clementine's cameras are co-aligned, so they're all looking at the same spot. So the near infrared camera would look at Nansen with a field of view like this. There's a near-infrared camera which operates in wavelengths just beyond the visible, and these are particularly good places to look at chemical absorption features, so to distinguish, say, one kind of mineral from another. There is a long-wave infrared camera which operates down near 8,000 or 9,000. I should say microns. I should say this in microns, right? Near 10 microns, near 9 microns, right? These are wavelengths which are good for looking at heat, at thermal emissions, and distinguishing, say, the thermal properties of one patch of soil from another. So it's a very different view than you get in the optical or the near infrared. There's also an imaging device aboard which doubles as a sensor for the laser radar. There's a laser radar or LiDAR aboard which can send out a laser pulse, and when it bounces off the thing that it's pointed at, the delay in the pulse tells you, of course, how far away the object is. Now, this used to be called a laser rangefinder, but since Clementine is now a scientific spacecraft, it's a laser altimeter. But principle is the same. If it looks down at the moon, this thing can fire laser pulses every once in a while and record the timing of the return of the pulse and gradually build up a lot of readings about just how high the topography is. Now, it's important to know that in the Apollo era, we didn't get a very good set of topographic measurements of the moon, and certainly not anything direct like a global laser altimeter reading. So this is a really novel contribution of Clementine. There was a laser altimeter flown aboard a couple of Apollo missions, but it only flew over a narrow region around the equator, so there's good accurate topography for those regions, but not for the poles or the high latitudes or what have you. So this gadget can be a camera, and it can take a high resolution picture of a tiny region in the center of the field of view. So it's not good for mapping because it doesn't overlap other high resolution pictures very well. But if you want occasional snapshots of regions, it does cover this narrow strip. And here's how all these pictures line up. Here's a map of the moon, which helps you figure out where this was. And the UV visible camera has this nice wide field. The near infrared has a somewhat larger fields, but approximately overlapping. The long wave infrared is somewhat smaller, and the high resolution is tiny like this. Some of the high resolution pictures can be made better looking than this one. This one wasn't processed very much, I think. And here are some typical pictures, mostly from the UV visible camera, of craters that Clementine sent back. Let's see, Chant Crater, thank you, in 40 degrees south, 190 degrees west. That's on the far side, I guess. And complicated the terrain. Freilich and Lovelace, two craters that are nearly identical with several peaks here. Peculiar. This is a view from the near infrared camera, and you can see that it's kind of noisy. There are bad pixels here and there, white specks that you can see in the picture. Copernicus crater, which is important not just because you can see it in a small telescope and it's a famous crater on the front side of the moon, but because Copernicus is the touchstone for lunar geology. It's kind of the first place where people really sat down in the 50s and began to figure out the story of lunar geology. Saying, oh well, let's see, the rain deposit from Copernicus splatters over this crater, so Copernicus must be younger than this crater. But here's a place where there's a crater that's clearly imposed on the Copernicus deposit, so that crater must be later. And flows of Mare material and the ages of craters and other features on the moon can be puzzled out to tell you something about the geological history of a piece of terrain. Well, Copernicus was the first place where that was studied, so it's always a good place to look at lunar geology. When you have a new spacecraft or a new instrument, you can bring the information you're getting into line with stuff that you know from other sources. Here's the same picture of Copernicus, but modified and superimposed on the topographic data, and then lined up nicely to make a swell-looking picture. And indeed, this is a frame from a QuickTime movie that cruises around Copernicus crater on the CD rooms. So we have topographic information to much better accuracy than before of Copernicus, and that's really useful in knowing in helping understand geological processes. Well, Clementine was not named Clementine for nothing. The folks that put her together felt that they would probably get a chance to do prospecting on the moon. That they could use the information from these fancy sensors to figure out something about the concentration of chemicals in lunar soil and the distribution of particular types of minerals on the lunar surface. So I put in this picture to remind me of that. This is a frame from Die Frau im Mond, the Girl in the Moon, right? Fritz Lang's great space movie that Hermann Oberth worked on in 1929. And in this story, there's a crazy professor who thinks that there's a reason to believe there's gold on the moon. So a spaceship is built, and the crazy professor and these other folks go to the moon, and the professor goes berserk and runs out of the spaceship, leaving footprints behind, and off into the wilderness with his dowsing rod to find the gold. And he does, but the villains get there first and so forth. Right? Okay. Well, Clementine can tell you a lot about the distribution of minerals, although I don't think it can find gold on the moon. I want to talk a little bit about that process because I find it interesting and because it's useful in a lot of other spacecraft studies. You'll certainly be seeing a lot of stuff when Bob gets to Jupiter later this December, and you will be seeing more multispectral pictures eventually of spacecraft and something about of the moons of Jupiter and so forth.
Get there vicariously, unfortunately.
Yeah. Okay. That's good enough. You know, look, I'm paying the taxes, right? I'm not going. So I don't care whether you go personally or whether you send some spacecraft there. I just want the pictures. Okay.
Check the World Wide Web.
Pardon?
Check the World Wide Web.
Check the World Wide Web, yes. Okay. The film at 11. Here's a wonderful PR picture of the surface of the moon near the North Pole, and a nearby planet which has some interesting terrain in various colors. Okay, right? All of Clementine's cameras, like all of Voyager's cameras or the solid-state imager on Galileo, are monochrome devices. They really take black and white pictures, right? And the way that we get color information out of them is to rotate a filter wheel, transparent filter that only lets through a narrow band of wavelengths. Okay, then you put pictures. Hopefully, you can make pixels more or less overlap, and you put these pictures together inside your computer. A black and white picture taken through a green filter, and a black and white picture taken through a red filter, and gradually build a color picture out of that. So here's what happens in that process when Clementine looks at the Earth. Clementine's UV visible camera looks at the Earth. Here's a picture taken at 450 nanometers, which is somewhere in the middle of the visible spectrum, I suppose, maybe green light or something, right? Maybe down towards blue. All right. The Earth is a planet which has some bright reflective stuff near the poles here and swirling around the middle, but it has dark material which absorbs blue light pretty well all through it. And you really can't see the distinction between, say, a continent and an ocean at this wavelength. But down in red light, this is actually just beyond the visible, but it's close to dark red, okay? In red light, the bright parts that were in the blue picture are still bright. So they're probably pretty reflective across the spectrum, and they would show up as white or gray in a colored view. But you can distinguish the continent of Africa from the oceans very well, because Africa reflects red light pretty well, especially in the Sahara Desert here and the drier parts down here. Not so good maybe in the jungle in the center. But it doesn't. The oceans don't reflect red light very well at all, or near infrared light. So so we can distinguish one type of terrain and one type of chemical substance on the Earth from another this way. At 900 nanometers, 950 nanometers, and 1,000 nanometers in the near infrared, we can see a marked contrast. The reason these filters are so close together in wavelength is that many minerals have important absorption features somewhere in there. And if you play with the ratios of reflectances in these three regions, you can learn a lot about composition and mineral types. Okay, so put some of these pictures together, and you can get a color picture where Africa's kind of tan, and the ocean is blue, and the clouds and ice caps are white. That is basically what is going on when people show you a quote multispectral or false color picture. Isn't it?
Question regarding the color pictures and black and white filters. I can understand from what you're saying why you do that. It's done for data. But have they ever taken a color pictures directly from color camera?
In interplanetary spacecraft?
Yeah.
I don't believe so. On the other hand, a color camera is sort of a cheat. I mean, down in the innards of a color camera, the same process is really going on. You know, there are tiny filters over the CCDs perhaps, or some arrangement like that.
Or a
I'm not real
prism.
Pardon?
Typically a prism
Typically a prism. Okay.
and 3 different sensors.
Mm-hmm. So you're the color. What we think of as a color TV camera is really making a picture out of probably 3 narrowband images and just doing the combining of the images closer and more in the hardware than we're seeing here. But it's also what you see on TV is probably in some sense just as much as a fake, and just as dissimilar to the color imaging in your eye as the as Clementine. But if you want to send a color camera, I think that, you know, if you ask an imaging specialist about this, they'll probably always pick the monochrome camera because they can probably control and understand the response of it much better, and it's less technically complex, except for the moving color filter. It's true. Anybody else got a question?
There was no yellow-green range filter used at all? Usually in popular, it's usually like a red, green, and blue.
I'll tell you this, I haven't memorized the table of filters available for Clementine, but actually it does appear in this picture. So if we really are desperate, we can figure this out. Here's a chart of wavelengths from say half a micron or so. That's 500 angstroms as I think about it from my education. I'm sorry, that's 5,000 angstroms, or 500 nanometers, which is what people are mostly saying out today. 5,000 angstroms or bluish, greenish light.
Yeah.
The filter we were looking at is the 415 nanometer filter, so I presume that that's this line right here, okay? And you can see that there are some other filter bands indicated as vertical stripes on this picture. Okay, and I mentioned that there were a gang of infrared filters that were clustered close together to pick up this mineral feature. I put this up because it shows reflectance spectra that happens when you go to the laboratory and you take the spectrum of various rocks that are typically found on the lunar surface or on the surface of asteroids. And it doesn't matter what these are, plagioclase, basalt, pyroxene, ilmenite, and so forth. But you can see that the basalt and the pyroxene have dips in the near infrared right around a little short of 1 micron, 1,000 nanometers. And plagioclase, while it's sloping downward, doesn't really have that dip. So you could distinguish these kinds of minerals from this kind if you could carefully measure the brightness ratios of your image in this region through these filters. And they have other distinct properties out here in the optical region, and ilmenite doesn't slope down at all. In fact, it gets more and more reflective as you go into the deeper infrared. So it starts out dark, but it's a little better out here, and you could probably tell ilmenite from these other minerals as well if you work on it. So that's a simple example of the tricks that people play with colors on the. My goodness, I have this sliding backwards. With colors on the lunar surface. This is a slide that interests me because it represents somebody I know who has exploited colors on the lunar surface to the ultimate degree. Peter Koch, who publishes the Moon Miners Manifesto, probably. How many know Peter Koch? An awful lot of people. Well known in the space movement. Peter got the idea maybe a year or so ago. He's always thinking about colonizing the moon and what people living on the moon would do, how they'd eat, how they would live, what kind of furniture they would sit on, how could they make things and make maximum effective use of the resources available on the lunar surface. And he was thinking about hobbies in art and decoration and such, and he wondered, could you paint on the moon? That is, would it be possible to make pigments and some kind of carrier out of lunar materials? And he began to look at the minerals available on the lunar surface, and found that there's quite a range of colors. He made his yellow out of sulfur, and he's got a number of other compounds that they've been determined. These are all really available on the moon. So he's been doing lunar paintings, and you can see them in the display room here. He's got a bunch of them on display. You can buy them, in fact, and I think this is a fascinating idea. But it suggests that the tiny color variations on the lunar surface might give you might give you a clue about different mineral composition. This slide isn't really oriented right. South is this way. Okay? Let's put this inside. I gotta label these better. But this is an example of the sort of work that geologists have been doing with the Clementine data. This is the Aristarchus Plateau, which has been studied a lot from telescopes on Earth, and which was a really interesting landing site with strange geology, and kept almost getting on the list for Apollo landing sites, but never quite made it. If there had been 2 or 3 more Apollo missions, probably one of them would have landed near Aristarchus. Yeah.
The red border, is that only because it's an incomplete mosaic? Or is that really a feature that straight?
Red border.
Yeah, reddish orange at the big, yeah.
This stuff here?
Yeah.
No, that's, you're looking at a distinct difference in chemistry of the mineral there.
Really?
Okay, that's well, no, it's all gray, actually.
Okay.
Okay, right, but some of it is a little
Yeah, but I'm
different
saying
gray than
but
others.
the chemistry between those two is
Yeah.
that, wow.
This is a distinction that Clementine's been able to make. Now, you can do some of this with a ground-based telescope too, but Clementine got much better spatial resolution. On the average, Clementine was in an elliptical orbit, so sometimes it was close to the moon, sometimes it was far away from the moon, but on the average, it covered the moon with about a 200 meter per pixel resolution. So what's happened here is we've taken the different reflectances of pixels in the images and in different wavelengths, and divided them so we get the colors are assigned not to how much 450 nanometers is there, but to what the ratio is between 450 and 750 or something like that. So there's blue areas probably have a lot more blue than red compared to the rest of the picture and that sort of thing. But here's the crater Aristarchus, which, as you see, is filled with blue stuff. And I'll look at the cheat sheet to see that is the material of the highlands on the moon, rather than the Maria. Mare material surrounds this plateau, and it looks kind of purplish or reddish if it's really old Mare material, and somewhat greenish if it's rather new, if it's newer. If it's old, it's been aged by meteorite attack and cosmic rays, and it has a slightly different color, slightly different appearance. And this red stuff is basically the result of volcanic activity spewing out material sometime long ago, and it covers the plain, and every once in a while an asteroid or something would bang into the moon and land and dig a hole, right, make a crater, and you could see the bluish island material underneath this base, okay, and the Mare material has flowed over that. So it's using these kinds of slight differences, we can just make a picture like this that gives us a clear signature for different kinds of minerals in a picture, and then use that signature along with other things that geologists know about the moon, and maybe including some of the topographic information to tell a story of how a particular piece of landscape got to look the way that it does. Don't have much time, but I'll cover a few other results. If you really are interested in lunar geology, you should look at the 16th of December issue of Science magazine, 16th of December 1994, because that's where the Clementine science team published their earliest results. And there are papers on some general stuff like, what did Clementine find about the global topography? What have they learned from the data set they've analyzed so far? And Clementine also flew around the moon and was tracked carefully by radar to look for Doppler shifts in signals, and this is the technique that you use to look for wiggles in Clementine's orbit. This was also used during the Apollo era, right? And the wiggles in the orbit tell you something about the varying gravitational attraction between Clementine and the moon. With this information, you can help figure out the moon's gravity field, and and that tells you where the heavy stuff is buried and where the spacecraft is flying over fairly light stuff. And that information is useful in conjunction with mineralogical information or topography to tell you the something about the global evolution of the moon. They also did publish a number of papers that were studies of particular areas like the Aristarchus Plateau or the South Polar region, or close studies of a few major craters, trying to see what they could squeeze out of Clementine data. And it will take many years, I'm sure, to analyze that, and pretty soon I'm sure the raw data will come out on CD-ROM and be available to scientists everywhere that want to work on lunar problems. But one problem that's of special interest to us is the South Pole of the moon. We've never had before good global accurate topography, and most of the topography of the moon has been done from photographs. So in photographs, it's relatively easy to show that one crater is deeper than the next crater over, or that the mountain is so high relative to the plains around it. But it's much harder to connect your photos from one piece of the mosaic to another and say that this spot at the North Pole is so much higher above sea level than this spot on the North Pole. Well, the moon doesn't have any seas, but I won't get into that in any detail, but they have a way of defining something like sea level. What they found, or one thing they found, was that there was a new basin that they hadn't ever really noticed before, or had scarcely been discovered. Wow, this is completely upside down, but that's okay because we're in space. Yeah, there was a large basin near the South Pole, so wide and deep enough that an awful lot of it is in permanent darkness, which is actually good news for us. There's something peculiar about this photo. It's pasted together from a lot of pictures of Clementine, so the sun has moved around, and all the shadows in this picture actually point toward the hole. So it's not a realistic picture. Here's the large crater Schrödinger, and so we didn't quite know where the low spots and high spots were on the moon very accurately, and the new information shows that there are some big, wide low spots, including one huge one that's 2,500 kilometers across, that have other basins and large craters and such superimposed on them. So they're very old, and we haven't noticed them before because they're obliterated by other parts of the landscape. But they're still big, low, shallow bowls, and some of them are even basins that have not even, well, like this one, haven't really been filled in by lava flows of mare material as the big maria on the front side of the moon have. So we're looking at a really primitive region of the moon in some sense. Well, there's a story that goes with permanently shadowed areas on near the poles of the moon, and you may have heard this story before. Comets probably hit the moon from time to time, right? It's never been observed, but there are comets in the solar system, and the moon probably gets one. A comet hits, it's made of ice, it's made of carbon dioxide, whatever. It vaporizes, and the moon, for a little while, has a temporary atmosphere. Not a very thick one, but some of the gas in the comet blows away immediately. Some of the gas in the comet takes longer to dissipate. And as the moon is gradually losing these molecules of gas, they're hopping around from place to place on the lunar surface. If they touch a hot place, then they probably are going to pick up some kinetic energy and bounce somewhere else or escape the moon altogether. If a molecule lands on a shadowed place that's pretty cold, then it'll probably stay there until it gets warm again, and sunrise comes, and the molecule gets warm and then hops to someplace else, right? If the molecule of gas winds up in a permanently shadowed place, it may stop in this cold spot and not have very much reason to leave again. There are other things that could make it go away, but there are far smaller forces than sunlight. So it's possible that that we could have a thin layer of frost left by the comet. Okay? And maybe sometime in the next century, another big comet comes along and hits the moon and makes a crater and vaporizes it somewhere. And another tiny layer of frost is added to these permanently shadowed regions. And over millions or even a billion years, possibly we have built up in certain spots at the North Pole and South Pole a layers of ice. Nobody really knows whether this is true or not. The scientists argue about it, and the evidence used to look about even until a couple years ago when radar discovered ice on Mercury. If it's on Mercury, maybe it's on the moon, right? And it would be very nice to fly an experiment to detect it. Again, it's worth expanding on, but I'm not going to do it today. That basically ice, water ice, or even carbon dioxide would be the raw material for rocket propellant. And this stuff could be an extremely valuable resource for a lunar economy, or for any kind of solar system economy that needed to gas up rockets and go somewhere else in cislunar space or in the rest of the solar system. And this is why people are so pleased on finding this in their finding lunar ice core at the South Pole. And it doesn't matter to them that the floodlights on their spacecraft are probably making this sublimate and go away.
Who's the artist on that?
One of the guys from one of the guys from what's the company that used to, one of Pat Rawlings' buddies, one of the people that used to work for Pat Rawlings. Geez, I'm sorry.
It's okay.
It's written on the slide. So pop it out and take a look. Here's a picture of Magellan, a radar satellite which has nothing to do with Clementine, except that that they did some interesting experiments with Magellan. You're familiar with the maps Magellan made with using its transmitter to bounce radar energy off of Venus and using its receiver to collect the radar energy. Magellan also did a couple of experiments during the end of its lifetime in what they call bistatic radar, and that is where the spacecraft uses its transmitter to shine energy on the planet, and a big, very sensitive receiver on a big dish back on Earth receives the radar energy. Okay? It's called bistatic because there are two stations. The transmitting station is different from the receiving station. Okay? Somebody got the idea of using, and this is kind of a last minute thing, of using Clementine's radio transmitter to shine energy into craters in the South Pole, into these permanently shadowed regions. And to use ground-based antennas to look at the radar return. Ground-based antennas get a view of the moon, of course, that's like this, right? But it's the view of the moon that you have. And they can't see the South Pole very well. And aiming a beam at regions near the South Pole, you'll be, the beam will be grazing across the ground, and one can hardly get much reflection. Whereas if Clementine went underneath the South Pole and shone radar on it, you get a lot more bounce back in the direction of Earth. It was kind of a kludge experiment, an improvised experiment. The system certainly wasn't designed for that, but radar reflection is one difficult way to tell something about the electrical properties of the material near the surface, and it seems to have pinned down ice on Mercury fairly well. Look at the polarization coming back, polarization ratios coming back, and see if we see ice on the moon. And there was a great deal of interest in this from the space activist community, because for years and years we've wanted to know whether there's ice on the moon, and nobody has flown a spacecraft with a more specific experiment that will tell us. Clementine did this. Rumors were going around that Clementine found ice, but in fact Clementine never announced that they had found ice, and to this day, as far as I know, they are still grinding the radar data. And there are still rumors that maybe one day they will announce that there really is evidence for ice. But if there's evidence for ice in that data, it's not really clear. It doesn't pop out. It's not obvious after only a short analysis. Okay, and
They've announced that the data are inconclusive.
they've announced that the data are inconclusive. Okay. Well, we have some reason for hope, and I realized that I should have brought. Oh, here's a ground-based antenna. I really should have brought some old Lunar Prospector slides along, but I don't have a modern picture of the current Lunar Prospector proposal. But the good news, as I mentioned before, is that Lunar Prospector is the next Discovery mission, which NASA will ask for a new start in, I think, in fiscal '96. Is that true?
I think so.
So it's a even less expensive mission than Clementine, perhaps, or maybe about the same cost in current year dollars. It'll cost about $73 million to fly it, including the launch. And Lunar Prospector will carry a gamma ray and neutron spectrometer aboard, which will be the right instrument for trying to detect the presence of hydrogen on the moon, and for the presence of ice. I don't know if I've got any more Clementine slides. We're about done. If we got, yeah, we're about done. Unless you have any more questions. Clementine took pictures of the Apollo landing sites. It's useful to know to take a look at places that you've actually visited, that you actually have rocks from, because you can compare what Clementine is seeing to stuff that you know from laboratory samples of these rocks. Here's the Apollo 16 landing site. It was between two bright craters. You can see a crater with some bright rays on it here. Here's a more close-up. The crater is here, South Ray crater. And between here and this other crater complex, here's the Clementine version of the landing site between those two splotches. Not nearly the resolution you would need to see any sign of the Apollo spacecraft or its landing splatter or the flag or anything, but it's nice to know that we can at least take a peek at these places once again. Here's the high resolution camera version of that. Doesn't tell me much, but I thought you'd like to see that. So there's a Clementine data set, and scientists are working it reasonably hard to get juicy initial information off of it, and I'm sure that it will provide fodder for lunar studies for a long time to come. And if indeed we get in 3 or 4 years a Lunar Prospector data set that has a lot of information about the global geochemistry of the moon, not just the ice question, but a completely different kind of information than Clementine about the composition of the soil and the particular distribution of certain elements around the moon, then we'll have a serious new input into lunar studies and a very good pair of precursors to any manned exploration that we want to do in the 21st century. Thank you very much. Yes.
Another question, point you might be interested in. Actually, an impact was sighted on the moon about 800 years ago. By 5 months crossing the field, they noticed a bright eruption on what would have been over the far side. And after we started exploring the far side of the moon, we noticed there was a very fresh crater there named Bruno, which was pretty much was almost the exact same spot where it would have hit.
They're really arguing over that one. The scholars do not. This story is by no means accepted by all scholars. I guess I'm on tape, so I should say the suggestion that 800 years ago some people really did spot an impact occurring on the moon with their naked eyes and recorded it in an old chronicle. And it's suggested that this is the crater Giordano Bruno. Probably. I guess I don't know the facts on that one either way, so I can't make up my own mind on it. I would have to look it up. I've heard it disputed.
Yeah.
Is there any likelihood that it would be estimated likelihood we actually build a third one in the next?
That's how big it is.
Oh, well, yeah, I'd say the likelihood is pretty good if a lot of people watch the moon constantly. And you could imagine building in your backyard, something that will watch the moon constantly. You could see an impact that was above a certain energy, right? It's a nice project.
Is anybody trying, anticipating it or looking at the an object coming in that would possibly affect the one?
Nobody has spotted anything like that. I think that it's possible that the asteroid collision surveys that people were talking about setting up in the near future might well find one that is due to hit the moon, but it's far more probable that they'll find one that's due to hit the Earth. So it's somewhat improbable that
He said you saw a
that they will find anything that's on the
Didn't
collision
even
course.
realize he was out there.
Can I take this off? Farewell to my tape audience. It was nice speaking to you, and we'll see you again in another year.